Today, we're diving into a paper that really changes how we think about solving some of the world's most difficult computational problems. The main idea? It's pretty radical. For decades, we've been trying to build faster computers, stronger algorithms, basically a bigger hammer to hit tougher nails. But this research asks a different question. What if, instead of building a stronger hammer, we could just reshape the nail? What if the secret isn't more brute force computation, but a smarter transformation of the problem before we even start?
You've probably felt this yourself. Maybe you're working on a puzzle, a logic problem, or even just organizing a complicated project. You're making progress, things are flowing, and then you add just one more little constraint, one more tiny variable, and bam! Everything grinds to a halt. You've hit a wall. And the weird thing is, the problem doesn't just feel a little bit harder, it feels completely, fundamentally impossible.
Well, it turns out that feeling is dead on. For a massive category of problems, the ones computer scientists call NP-complete, this is exactly what happens. Now, these are problems where if someone gives you an answer, it's super easy to check if it's right. But finding that answer in the first place, that can be brutally, exponentially hard. And for these problems, the difficulty doesn't just ramp up smoothly. As you make them more complex, you reach a tipping point where solvability just falls off a cliff.
The researchers in this paper actually give that cliff edge a name, the Chang-Bell point. And this isn't just some abstract idea. It's a measurable structural characteristic inside the problem's data. You can find it. It's the precise boundary line between a problem that's manageable and one that's a nightmare. Understanding where this point is and why it exists is really the key to this entire approach.
A radical new approach. So, knowing that this computational cliff is out there, how do we avoid just walking right off it? Well, this paper suggests we should stop trying to build a bridge over it and instead completely reshape the landscape so the cliff is in a different place, or maybe not so steep.
And this right here, this is the heart of it all. Transformation precedes computation. The whole argument is that before you throw your supercomputer at a problem, before you run a single line of solver code, you should first transform the problem itself. It's a shift in focus. We're not trying to make the solver smarter, we're trying to make the problem simpler and clearer.
To actually do this, the researchers came up with three really distinct methods. Think of them as three different lenses you can use to look at and reshape a problem. And each one of these lenses is borrowed from classic fields like physics and mathematics, but they've been cleverly repurposed for this brand new task.
Now, before we look at what makes each lens unique, it's really important to get that they all follow the exact same three-step process. First, signalization. They take the problem, whether it's a bunch of numbers or a set of logic rules, and turn it into a continuous signal, kind of like a sound wave. Second, domain adjustment. This is where the magic happens. They take that signal and move it into a totally different mathematical space, like the frequency domain, and tweak it. They filter it, smooth it, or adjust it. And third, discrete remapping. This part is genius. They take that modified signal and carefully convert it back into a version of the original problem, making sure all the fundamental rules are still intact. The problem is different, but it's still valid.
So, what are these three lenses? First up is Fourier-Guided Preprocessing, or FGP. I like to call this one the pattern finder. It uses the Fourier transform, a tool that breaks down signals into their component frequencies, to find the dominant patterns in the problem's structure and filter out the distracting noise. Next, we have Laplace-Guided Preprocessing, or LGP. This is the global smoother. It views the problem as a network or graph and essentially blurs out the tiny, local details, which helps reveal the broad, big-picture shape of the problem. And finally, Entropy-Guided Preprocessing, EGP. This one is the disorder thermometer. It uses ideas from information theory to measure the chaos or randomness inside the problem. It finds the hotspots of disorder and then reorganizes the problem's parts to be more balanced.
Right, so just to sum that up quickly, FGP works in the frequency domain to filter patterns. LGP works on a graph to smooth out the structure. And EGP uses entropy to measure and rebalance disorder. Three very different approaches, all aiming for the same thing. So how did they actually do in a head-to-head test?
Okay, the theory is really cool, but let's get to the real question. Does this stuff actually work? To find out, the researchers threw these three lenses at some classic and famously difficult computational problems.
Their first guinea pig was the subset sum problem. It's a pretty easy to understand puzzle. You get a big list of numbers, and you have to figure out if any combination of them can add up to exactly a target number. The key thing here is that the problem's structure is all about the numerical values themselves. It's continuous. You can have big numbers, small numbers, and everything in between.
The results were pretty cool.
This chart shows us that computational cliff, that Chang-Bell point we talked about. For the original, untouched problems, the cliff appears when the target value is around 420. But check out what happens after they run the preprocessing. The Fourier method, for example, shifts that cliff way down to 362. Basically, all three methods successfully change the problem's DNA, making that tough transition zone more manageable. A definite win.
Okay, so if all three methods worked, then what's the big deal? You might think they're all equally good, but the researchers had another test up their sleeve, a totally different kind of problem, one that was specifically designed to expose a critical and potentially fatal flaw in some of these approaches.
For their second test, they used the Boolean satisfiability problem, or just SAT for short. Now, this is a completely different beast. It's not about numbers that you can add up, it's a pure logic puzzle. You get a long, complicated statement full of variables, and you have to decide if there's any way to assign true or false to those variables to make the whole statement true. Its structure is discrete and combinatorial. The rules are rigid, you can't bend them. And the results this time were just, wow, absolutely dramatic. You can see on this chart, the original, raw problems were mostly solvable. And the ones transformed using EGP, the entropy method, were also fine, still solvable. But the problems that were pre-processed with the Fourier and Laplace methods, it was a complete and utter disaster. They became almost entirely unsolvable. So what on earth happened? This quote from the paper nails it. The structural integrity of the problems was severely damaged. Remember how FGP and LGP work? They filter and smooth things. But you can't smooth a strict logical rule like A must be true. It's either true or it's not. There's no in-between. By trying to apply their blurring and filtering techniques to this rigid structure, they didn't simplify the problem, they just broke it.
And that leads us to the most important finding of the whole paper. FGP and LGP, our pattern finder and global smoother, are great for problems based on continuous numbers, but they fail spectacularly on discrete logic problems because they shatter their structure. EGP, the disorder thermometer, was the only one that succeeded on both. It managed to reorganize the problem's components and shift its difficulty without violating its fundamental discrete rules. This makes EGP a much more robust, universally useful tool.
Okay, this is a really interesting discovery for computer science theory for sure. But what does it actually mean for the real world? This is where the paper takes a really exciting turn, pivoting away from just solving puzzles and towards the future of artificial intelligence.
The researchers make a powerful argument here. They say the biggest prize isn't just a new tool for solving one problem. The ultimate goal is to use these transformation techniques to generate massive data sets of what they call clarified problems. We can create millions of examples of problems at every level of difficulty, which can then be used to train AI models to understand problem structure at a level we've never seen before.
So how does this lead to smarter AI? Well, first, it generates much clearer training data. Second, we can use it to specifically create tons of examples right on the edge of that changeable region, teaching the AI to recognize what the hardest parts of a problem look like. And maybe most importantly, we can create a rich data set of failure patterns. We can show the AI not just how to succeed, but precisely why and how a problem becomes unsolvable. Ultimately, this teaches an AI to see the deep underlying structure of a problem, which is a far more powerful skill than just recognizing surface-level patterns in existing solutions.
And this isn't just some far-off academic dream. To make sure this work has an immediate impact, the researchers have already released their tools as ready-to-use code in 3 of the biggest programming languages out there, Python, Java, and C. So anyone in industry or academia can start experimenting with this today. And that really leaves us with a huge, exciting final thought. For decades, the entire field of AI has been focused on building better solvers, AIs that can crack the tough problems we give them. This research points to a whole new horizon. What if the next giant leap in AI isn't a better solver at all, but a better transformer? An AI that doesn't just throw itself at impossible problems, but one that has learned the art of making them simple in the first place.